it is a continuation of section 5.3, diagonalization. Let's see this example. Diagonalize the following matrix if possible. To diagonalize the matrix, we have to first find the eigenvalues and eigenvectors. So start with here forming A minus lambda I, 3 minus lambda, 0, 0, 1, and 0, 2 minus lambda, 0, 0, and 0 again 2, okay, not here, and there must be 0, and for that one it becomes 2 minus lambda and 0, and 1, 0, 0, 3 minus lambda. Okay, from this matrix we have to find the determinant. Okay, so here now determinant of A minus lambda I, that is, now we'll use the coefficient expansion. Okay, for example, we may try to use this one, then now in row or column every else 0, so that will become 2 minus lambda is 2 position, so we don't have to worry about the sign, and then the remainder part is 3 minus lambda, the submatrix. Okay, erasing this one. Now this is 0 and 1, and 0, 2 minus lambda and 0, and 1, 0, 3 minus lambda. Okay, so we have to find the determinant of this matrix. Again, we'll use this one, that one, coefficient expansion along the row, then these times, and the determinant of the remainder. So that will be now 2 minus lambda squared, and now sign must be 1 minus 1 to the 1, 2 plus 2, and the submatrix will be 3 minus lambda and 1, and 1, 3 minus lambda. Right? So from here, that is 2 minus lambda squared, and this portion is same as now 3 minus lambda squared and minus 1. So that is now 2 minus lambda squared, and this one is now lambda squared minus 6 lambda, and plus 9 minus 1, so that plus 8. Now we have 2 and 4 separation along with the negation here, so that we can get here, that is lambda minus 2 squared, so lambda minus 2 squared and 1 more, so third power, and lambda minus 4. So we have here the eigenvalues, lambda equal 2, 2, 2, and now 4. Okay, we found the eigenvalues. Now we have to find the eigenvectors. Okay, let's begin with here lambda is 2. Okay, lambda equal 2. Then A minus lambda I, we subtract 2 along the diagonal. Then there's 1, 0, 0, 1. Now 2, so that is a 0, 0, 0, 0. Again, one more 0 row, and this is 1, 0, 0, 1. Okay, 2 0 rows, and these two are the same. So when we try to solve this matrix x equals 0, the homogeneous system, then by using the elementary row operations, we reach this one, 1, 0, 0, 1, and now the same, so after, so it will become again 0, so that here we have 3 0 rows. Okay, that's the reduced echelon form. And x2, x3, x4 are free variables. Okay, so here x1 equal same as that one, same as minus x4, right? And x2 is free variable, x3 is again free variable, x4 is again a free variable. From here, x can be written along with x2. We have a vector 0, 1, 0, 0, 0, 1, 0, 0. Now, with x2, it's x2, and now along with x3, right? And 0, 0, 1, 0, 0, 0, 1, 0, and with x4, that's minus 1, 0, 0, 1, minus 1, 0, 0, 1. Okay, we found 3 linearly independent eigenvectors for lambda equal 2. So already we know is diagonalizable, because with lambda equal 4, we'll get 1 linearly independent eigenvector. Okay, let's finish computation. Lambda equal 4. Then we subtract along the diagonal. Now 4. Then, okay, here we have the original matrix now 3, 2, 2, 3. Okay, we try to subtract 4 along the diagonal. Okay. Okay, here. So that is, this position is 3, so that minus 1, 0, 0, 1. This is 2, so the 0, minus 2, 0, 0. This position is 2, so the 0, 0, minus 2, 0. And 1, 0, 0. That is originally 3, minus 4 is minus 1. Okay. Now again, we have to solve this homogeneous system. Now we can use the same technique, elementary row operations. From here, these two are essentially same, so we can make it 0 by adding this one here. And with the scaling, it becomes 1, 0, 0, 1. Now after scaling, it becomes 0, 1, 0, 0, 0, 0, 1, 0, and final one is the 0 row. Okay. Now from this one, from this one, we can say x1, okay, x4 is free variable, minus x1 is minus x4, and this means x2 equals 0. That means again x3 equals 0, and x4 is free variable. Okay, from here, x is now with x4, direction is minus 1, 0, 0, 1. Okay, that is now, okay, this one is, just a moment, we forgot here. Okay, that is, okay, after scaling, there must be minus 1, so that must be positive. right? Okay, so 1, 0, 0, 1, 1, 0, 0, 1, right? So if we collect these four, and this vector, that one, and that one, they are linearly independent. And again, this one is linear independent from these three vectors. So we collect them here. That will be P. And with the same order, we put here 2, 2, 2, 4 for diagonal matrix D. Then the given matrix will be P, D, P inverse. Okay. An n by n square matrix with n distinct eigenvalues is diagonalizable. That theorem is quite simple conclusion that for distinct eigenvalues, if we consider the corresponding eigenvectors, then they are linearly independent. So if we have n distinct eigenvalues, then the corresponding eigenvectors must be linearly independent. That means we have n linearly independent eigenvectors. So it is diagonalizable. Determine if the following matrix is diagonalizable. Okay, for that one, this is upper triangular. So the diagonal entries are eigenvalues. So we have eigenvalues 5, 0, and -2. So it is diagonalizable immediately. And for that one, you can find the corresponding eigenvectors. For that one, let's try to find the eigenvector. Lambda equals 0. Then a minus lambda I, that is the same as original one, original metric, 5 minus 8 and 1, 0, 0, 7, and that is now 0, 0, minus 2. Now we have to solve this homogeneous system. And again, we are using the same technique, elementary row operations for the augmented matrix, but the extra column will be 0 so that we ignore it. From the matrix, now after scaling, this 2 will become 1. So we can eliminate this one, and then we can eliminate that one. So we reach at 5 minus 8 and 0, 0, 0, 1, 0, 0, 0, right? After scaling, we can get reduce the echelon form from this one. There's now 1 and minus 8 over 5 and 0, 0, 0, 1, 0, 0, 0. Now we have the reduced echelon form, and x2 is a free variable. So here x1 is same as from this one is 8 over 5x2. x2 is a free variable, and that means x3 is 0. So from here, now x is, along with x2, free variable, and there is 8 over 5, and this is 1 and 0. So that is eigenvector corresponding to the eigenvalue 0. And for two others, you can find eigenvectors, and you can finish yourself. Matrices whose eigenvalues are not distinct. A is an n by n square matrix whose distinct eigenvalues are lambda 1 to lambda p. And EA, lambda k, is the eigenspace for lambda k. of A. So for matrix A and an eigenvalue lambda k, we use the notation E sub A lambda k for the eigenspace. Here, dimension of the eigenspace is less than or equal to the multiplicity of the eigenvalue lambda k. And that means that for each lambda k eigenvalue, the eigenspace dimension is less than or equal to the multiplicity. That means here, once, for example, multiplicity of lambda k is 2, then you can find the maximum 2 linearly independent eigenvectors for the eigenvalue. And earlier, when we solved the examples, and we found that for an eigenvalue of multiplicity 2, we can find only one single eigenvector. Like that, the number of linear independent eigenvectors cannot be larger than the multiplicity. The matrix is diagonalizable. Then here, the sum of dimensions of the eigenspaces equal to n. In this case, it has n linearly independent eigenvectors, because the dimension of each eigenspace is decided by the number of independent eigenvectors, so that the sum of dimensions of the eigenspace equals n is the same as diagonalization of A. If it is happening, then for each eigenspace, the inequality must be equality. So dimension of each eigenspace must be same as the multiplicity of the eigenvalue for every eigenvalue. And in this case, here we have the number of linear independent eigenvectors become n. Okay. Here, if A is diagonalizable and BK is a basis for the eigenspace of lambda k, then the total collection of vectors in the set form a eigenvector basis for Rn. Okay. Now, once it's diagonalizable, that means that there are n linearly independent eigenvectors. So each eigenspace has a basis, and these are eigenvectors. And now they are linearly independent. If we collect them, then again, this is linear independent n eigenvectors, so that this set forms an eigenvector basis for Rn. That's really simple consequence. Diagonalize the following matrix if possible. Okay, for this matrix, because it is a lower triangular matrix, we can easily see that these 5, the diagonal entries, are eigenvalues. So we have here eigenvalues are 5, 5, and minus 3, minus 3. Okay? So we have to find the corresponding eigenvectors. Okay, let's begin with lambda is 5. A minus lambda I 5 will be subtracted along the diagonal, so that is 0, 0, 0, 0, and again one more 0 row, and 5 is subtracted 1, 4, minus 8, and 0, and this is minus 1, minus 2, 0, and minus 8, right? Okay. Now we have to solve the homogeneous system like that. And now how? Again, we are using the same technique, elementary row operations for the augmented matrix. But because of 0 row, extra row, we ignore this augmented part. And for the matrix, here we apply elementary row operations. Okay, we can move this one on the top. 1, 4, minus 8, and 0. And we add over there, add. Then there will be 0. There will be 2. There will be minus 8, and again minus 8. And we have 2 0 rows. Now, okay, we can scale. Then it will become 1. Okay, let's try to overwrite. And so that there is a 0 and 1, minus 4, minus 4. Rather than this one, we consider that. Okay, from this one, we subtract 4 times of the second row to make it 0. Then 1, 0. 4 times subtracted, which means 16 is added. So it is 8. 4 times subtracted, 16. Now that is 0, 1, minus 4, minus 4. And then 2 0 rows. Okay, let's go back to blue. Now, from here, this is the reduced echelon form, and x3, x4 are free variables. And from here, x1 equal minus 8, x3, minus 16, x4, and x2 equal 4, x3, plus 4, x4. And x3 is a free variable, so x3 is x3. x4 is another free variable, so it is x4. Now, from this one, here we can conclude x is, along with x3, the direction is minus 8, 4, 1, 0. Minus 8, 4, 1, 0. Plus x4, along with x4, we have now minus 16, 4, 0, 1. 4, 0, 1. So we found 2 linearly independent eigenvectors. Now how about for lambda is minus 3? Okay, here lambda is minus 3. Okay, for that one, we have to add 3 along the diagonal for a minus lambda I. We add 3, then that is 8, 0, 0, 0, 0, 8, 0, 0. We are adding 3. So 1, 4, 0, 0, and 1, minus 2, 0, 0. Okay. Now we have to solve again this matrix times x equal 0, a homogeneous system. Again, we are using the elementary row operations. Okay. Now from here, okay, we can scale this to 1 and 1. And along with 1, we can eliminate this one by subtracting. along with this one, we can eliminate this one again, so that if you do the detailed computation, you can reach at here 1, 0, 0, 0, 0, 1, 0, 0, and here 2 0 rows. You can get it quite easily. Now, that means here x1 equals 0, and x2 equals 0, and x3, x4 are free variables. So x3 is x3, and x4 equal x4. So we have here, now x is, okay, x is, okay, for along with x3, we have, now first two must be 0 and 1, 0. And with x4, another free variable. Now first two must be 0. And again, this is 0 and 1. Okay. So we have 4 linearly independent eigenvectors. Here we have 1. And along with and another one, along with lambda equal 5. And we have now 2 more here, along with lambda equal, okay, I forgot, what is that? Okay, minus 3, okay, minus 3. So if you collect these 4 in this order, then your D must be here diagonal of here 5, 5, minus 3, minus 3, right? Then we finish the diagonalization. Okay. Okay, we have here now true or false problem. A is diagonalizable if A is PDP inverse for some metric D and some invertible metric P. Is it true? It's false. It requires D being a diagonal metric. If you choose arbitrary metric D, then it is not a diagonalization. So D must be diagonal metric. So the given statement is false. If Rm has a basis of eigenvectors of A, then A is diagonalizable. Is it true? Yeah, it must be true. Rn has a basis of eigenvectors of A means that there are n linearly independent eigenvectors, so it is diagonalizable. If A is diagonalizable, then A is invertible. Okay. This assertion may be a little bit hard to answer. Is it true? Here, okay, to answer for that one, and we'll go back to an example we solved them. Okay, for that one, eigenvalues, this one, and there are 3 eigenvalues, 5, 0, minus 2. They are distinct, so that we'll have 3 linear independent eigenvectors for this matrix. So it is diagonalizable. Now, is it invertible? No. The determinant, if you try to get determinant, then the multiple of diagonal entries is the determinant. So the determinant is 0, which means A is not invertible. However, it is diagonalizable. Right? So the statement we are considering is false. Now, how about the opposite? If A is invertible, then A is diagonalizable. Okay, for that one, again, let's see one example. It's invertible, okay, but it's not diagonalizable. We will see one example. Okay, where is the example? It's invertible, okay. Okay, let's go back further. Okay, for this one. Now, this one is invertible because the eigenvalues, their product is 4, which means the determinant is now 4. Determinant of a matrix is 4. So it is invertible. However, now for lambda is -2, we have only one linear independent eigenvector. If we can get one eigenvector from lambda is 1, then the total number of linearly independent eigenvectors for the matrix is 2. So it is not diagonalizable. This is invertible, but not diagonalizable. So again, the statement is false. Okay? So from these two statements, we can conclude that diagonalization and invertibility are independent concepts, so that one is not implying the other. They are independent. If AP and PD with D diagonal, then non-zero columns of P must be eigenvectors of A. We considered this one from a remark, so it is true. Right? Okay, that's the end of section. Thank you.